what we're going to be going over here is a determinant, and we're going to be looking at it in terms of a Hessian matrix, which really is just a change in slope here. And we're going to look at this determinant through a multivariate solution here, and we'll be looking at it really as a visual perspective to understand what the determinant is. And we'll look at it in terms of the production function, and that's really similar to the Cobb-Douglas production function. Okay, so the production function we're going to be working with here is we're going to have some revenue output here, $1,400 here, unit price of the product we're selling times some material and labor inputs here raised to some exponential amounts, and then we'd be subtracting it from that the cost or the budget constraint, and we'll have some material cost here, $350 per unit of material minus $200 for unit per labor, and then we add in our cost constraint here. So first off, we'll just go through this here. We don't want to get lost in the numbers here, but we just want to find out where our numbers came from so we can understand this determinant that we're going to be looking at. So the first thing, based on our production function here, we have to set up a Lagrangian equation here. So what I'm showing here is the revenue portion here. And then we add to it, and this is where we add in that Lagrangian multiplier, the lambda here, times our cost or our budget constraint. And you can see our constraint here was $40,000, and then we'd be subtracting our labor and material inputs, and that's all times our Lagrangian. So then what we do with this Lagrangian equation here, we'll take the partial derivative with respect to labor, material, and also the Lagrangian itself. So, and this is the first partial derivatives here. So for our labor here, in terms of our Lagrangian equation, I've got that shown over here. I'm not going to get into these numbers here specifically, but just understand where they came from. And then for our material, same thing, go through, take the partial derivative of the entire equation here for material, and then we would do it for Lagrangian multiplier as well. Just take the partial derivative of this equation here in terms of a Lagrangian multiplier. So we have three first partial derivatives that we take in here for labor, material, and then the Lagrangian multiplier itself for the cost portion here. So we have three equations, three unknowns here. We don't know our labor, our material, and then our Lagrangian multiplier. So we put this into, in this case I'm just using MapleSoft here, come up with a solution here, and based on those three equations, three unknowns, we'll have some solution here. A certain amount of labor, 78 units of labor, point some fraction. Material, 69 units here times some fractional amounts, and then the Lagrangian multiplier. Okay, so the first thing we have to do when we're talking about this determinant, we're talking about matrices. So here's where we're going to be setting up what they call a Hessian matrix, and that's really taking the second partial derivatives here based on our first partial derivatives based on a production function. So just understand how that's set up here real quickly here. So we have a zero amount here. That's really origin that we're looking at. And then for our first row here, we'd have a g of the second partial derivative of our cost function here, a gxy cost function in terms of y, 200, g of x here in terms of that cost function in terms of x, 350. And then let's just go down our first column here. Same thing, just plug it in here, g of y, 200 for first column, and then 350 g of x here. So then for our second partial derivatives for looking at it, I just kind of color keyed in here, f of yy, that's our labor here. We take our second partial derivative in terms of labor, and we get that. And then moving over to our function here of our f of y, x here, that labor portion here, that we take our second in terms of x here. First one was for labor, and then for our x, our f of xx here for material, first f of x in terms of y here, this row here, and then f of x in terms of x itself here for that part of the part here where we're talking about our material. First derivatives, partial first derivatives here, we turned all those partial first derivatives into this Hessian matrix here as partial second derivatives here. So then, what do we do here? Just put that into the computer here, and it's going to give us a solution here, and I'm asking for a solution here in terms of algebra. So we're going to have, you can see, material and labor here. We got three different multivariate determinants. This is really the determinant. This is the solution, and this is the determinant in terms of the algebraic solution we're looking at here. So that's what you're going to get based on doing your determinant here based on your Hessian matrix that we set up. So this is a 3 by 3 matrix. Three columns here, and 3 rows across here. So then, the other thing is, when you're dealing with determinants, we would put in that those specific numbers that we're looking at here, that solution amount here, into this determinant here, and it's going to give us a determinant in terms of scalar amounts here. We're going to get these quantities here. We're not going to be dealing with those in this presentation here. That we're going to have this, you'd come up with a 3x3 determinant matrix here based on the specific solution we looked at that specific point. So your determinant is really a matrix or block of numbers here, and then that matrix here, when you solve it, it comes into a single number here, in this case 497,300 here, and that's really a single number and really represents a volume here. Okay, so that's the basis here for coming up with the numbers that we have to look at. But what we want to deal with is this determinant here in terms of the algebraic solution here of this Hessian matrix or the second partial derivative. So this is what we're going to be working with here, this algebraic solution here. Okay, so let's go back up here and let's look at what we're talking about. So that production function we're talking about, I'm showing here, revenue minus our cost here is really represented by this blue here, and I've got those ISO lines put in here. And really we're going to look at 3 different points here on the blue here is, remember that's our production function here. And then we're going to be looking at 3 different points here. Okay, we're going to 1, 2, 3 here. So what these points are here, they're following up a gradient path here. That's where we have the greatest increase here. So we're a production function, we're looking at some increases along a gradient path. And that is, gradient here is something perpendicular to the ISO curves that we're talking about. Okay, so that's our production function here, and we're going to go down here. And when we're talking about this Hessian matrix, really we're going to be concentrating here on the determinant, but just to understand a Hessian matrix, that's that second partial derivatives that we set up. It's really looking at curvature here and the change in slope. Okay, so let's go look at our production function over here. Just looking at a side view, and I took out the blue portion here, and all I'm showing are those 3 points that we're going to be looking at here. And that falls around our gradient path here. That's where we have the greatest increase or the greatest output. So looking at transferring this first point down here, but looking at our side view here of our production function, we got really steep increases here, represented by these arrows here. And then I've got it graphed around those specific points. I've got the production function graphed around those specific points. So as we move up here, we kind of start leveling off here. We have a very steep ascent here, and then we kind of level off here. And then we have some point here. I'm just showing on our gradient path here. And again, you can see how this the Hessian matrix, or these second partial derivatives, are really looking for the change in our curve here. And then as we move down, you can see it's moving down here. But in this case, both our curvature here is pointing upwards here when we look at it in terms of this specific point here. If we looked at this point here, then you could see it be going down here and sort of coming up here. Okay, so that's for looking at our gradient path here from a side view. So let's just look at the end view. Again, looking at that just say these points here, and I'm looking, just say at one of those points on our curve here. So with this gold mesh part here with that second point here, you can see here the curvature would be moving upwards here, Okay, and you'd have that for all of your points. Okay, so how does that all fit into the determinant? Okay, so what I've done here, that determinant here, that algebraic solution, you can't really see it, but that's what I have here. What I've done here is I've plotted that out here, and it's shown with this green, and it's kind of have a mesh background here. That is the determinant. That is our solution here, that multivariate solution here of our function, that function here, the change of f and x and y and that determinant here. So that's our change, that whole green area here, and you can see it's got a shape to it here. And along with that, what I've done here is I put in the path. That's that same gradient path. It would be the path that would be equal to the production function path that we showed up above here. And I'm just showing 2 points here. There's one way up over here. But you can see, you start out with a very steep, in case as above here we were going up, here we're just going down here. Real steep ascent, and then it starts leveling off here for a different different points, the second and third point here. So we're really looking at the change in slope here, or the rate of change here. All right, and just looking at it in terms of that mid-range point that we're looking at up above here. So kind of interesting just to look at it in terms of graphing it out here based on our solution here. So generally you're working, when you're talking about determinants, you have matrices and blocks of numbers here, and in this case we're working off the determinant as an algebraic solution. And again, if we go down here, you're going to see it's really a scalar number that we're talking about. At any point here we're looking at a volume of this determinant of this function here. It's actually a volume, or height, width, length, volume here. And that really, that was that scalar number, that 497,300 at the specific point of 69.68, 78.04. And that's that point right here. So this determinant has a volume, and really we're looking at the change in volume here. So we would have a real high volume up here where we start out with that steep descent. In this case, we had, looking up over here, we had that steep ascent. Here you got a steep descent. So they're just sort of working, they all come up with the same numbers, or not, they're scalar, very much different scalar-wise, but just making a point here. One is going up, this one is coming down. And you can relate the two. And they share the same gradient path here based on that number that we come up with for the Lagrangian multiplier, or that's the point. Those are the points where we come up with our maximum change. So if we move over here, you can see, again, I got them piggybacked here. I just took that production function here and I got it plotted underneath. You can see it's kind of moving upwards here, whereas our determinant is moving down. They all share the same points here. Well, they have different numbers here, and the determinant is really a change in slope based on volume, whereas our production function here, I'm showing a production function here, it's really derivatives here, and it would be a directional derivative of some amount or some quantity as well here, but that is really a single number here, where our determinant is really a change in slope here. Just to understand it, get to see what they are here. Okay, so you can see they piggyback, or the determinant is coming down here, where it means it's decreasing here, and our production function is going up, and it's also decreasing. We start out with great amount here, and then we start leveling off here. Whereas our determinant, again, we start out with a great amount here, and then we start leveling off. So they level off, they fit into, or they fit over each other here, exactly over the top of each other here. Just showing it. Okay, so now we'll go on and we'll look further at our visual understanding, and then we'll do some calculations. Okay, now we'll look at it pictorially, and we'll start out looking at it in terms of the gradient field. So starting with our production function, I've got that shown here, and the gradient path is shown up along here. But I plotted in these arrows here, and those yellow arrows, those sort of 3D arrows in here, they show the direction of the greatest output, or the greatest profits that we'd have here. So you can see here at the beginning here, where you have your initial production numbers here, and as you increase, you can see you have your greatest output or your greatest profit here, showing by the size of those arrows here. So as you move up farther and farther here, you have smaller and smaller arrows. Actually, they're hid here. Okay, so you get the idea what's going on as far as your gradient field, or the direction of your greatest output here. All right, so comparing that to our determinant moving down here, and I've got the determinant again plotted out here in green here, sort of a mesh area. And my gradient path here is shown by those blue spheres, and those are yellow spheres here are those different outputs that we're looking at. This is our mid-range output, and this is way when we have that greatest, the largest output that we're looking at. But again, here's where I put in and I graphed in our gradient field into that, and it's shown by these yellow sort of 3D arrows. See, they're pointing in the direction here of the greatest output here. So up above you had it, it's kind of moving in the other, just moving up here, you're moving in this direction. Now when you're looking at it in terms of your determinant here, and remember the determinant is the rate of change, and it's really volume related, so that's what we're talking about, these yellow arrows. But you see they're sort of slanted, they start out at a sort of medium amount here, and then as you move in this direction or move along, and I don't know if that's the M or the L here, but you'd have to plot that out here, you get a greater increase. The larger arrows, it's pointing in the direction of the greatest increase here, and it's slanted here. You're having a greater increase here than you are over here. And then if you move in this direction here where we're having that larger output or larger quantities that we're looking at, you see your gradient. You virtually can't even see the arrows here. And then remember this determinant here, that was our multivariate solution. That one's showing down here, those at algebraic term here. Okay, so as you can see here, but nonetheless, you have your greater increases here. They sort of match up, but the arrows are going in different directions if you compare them to your graphing your functions. Okay, so that's our gradient. So let's go up our gradient field here. So let's go up and let's look at, compare our production function here to our determinant here. So for our production function, I'm showing those 3 different points here. So you get that the gradient path here. You have a great increases here when you initially have your first quantities produced, and then as you move up and along here, you get lesser and lesser increases, looking at those 3 points. So these are really tangent planes, those 3 different, at each of these points here, that meshed area, those are tangent planes. And you can think them as 2-dimensional here. They have a scalar amount, but they're really a 2-dimensional scalar amount, although they 3 dimensions here to draw them, but they are sort of 2 dimensionals, x and y here. Okay, and then if you compare it to our production function going down, or excuse me, our determinant going down here, I've graphed out these, matching them, tried to match them side by side. The determinant here, that yellow sphere here, that matches up with our first point here in our production function. And then as we go down here, we get down to, this is where we get into the determinant, that is that production, or that is our determinant multivariate solution that I've graphed out, thing we've been looking at here. So you see that it moves down here, or decreases at a very fast rate here. It's decreasing, and then it gets to our second point here, kind of levels out, that matches to our mid-range and our production function, and then it moves over here. So you can see the paths, how they're working here. The production function is moving this kind of greater increases here, but then it levels off. Same with our determinant function. Greater decreases essentially, and then it levels off here. Okay, so that's our paths here, looking at them. Okay, now let's just move over here. Now we were talking about those 2D tangent planes over here on our production function. So what I've done here, I've just taken that mid-range point here and I plotted it on our determinant function here. And you see what I have to do is I have to come to the underside of the determinant function, because that's where it's tangent. It's not tangent on the top side, but it's like the production function. It's tangent on its top side. Well, the determinant here is tangent really on the bottom side, because that's where you get it. You wouldn't see it if I plotted those looking down into that determinant function here. So it's on the bottom side, and this really, the only point I'm making, these are really 3-dimensional. These tangent, they're tangent volumes, I like to call them. You can see they're 3-dimensional, but they have an x, y, and a z value essentially. So they present a volume here. And then if you look at it moving down here, just looking at those 3 points here, those tangents, determinant, these are the tangent volumes or tangent planes that have value to them, showing them here. Starting over here, first point, then it decreases and so forth here. And I just laid those on top of the production function here, just moving that up and down. So you got the gradient or the rate of change here. We have our greatest increases here for the production function here, and greatest decreases here for the determinant here, where we start out. And then they level off and they sit on top of each other essentially, based on our solution. And then if we go down over here, just looking at it from a side view, getting a side view here. So we got our determinant or the change here in our volume, starting with our point determinant function here. That yellow one's showing here, and those blue, that's our gradient path essentially for a determinant, and then our production function shown underneath here, that red one. So that you can see that's coming up and leveling off. Our determinant is decreasing at a fast rate and leveling off. Production function increasing and leveling off. And then again, remember that production function, just looking at it relative to it here. You got a real steep increase here, and then that second point here, sort of lesser and lesser decrease, and then it levels off here. I'm just showing it in respect to those 3 points that we're looking at here, and you can see it levels off here. That was our function here, our revenue unit amount for our units for our revenue here, and then subtracting out our cost. Okay, so now we'll just move on and we'll look at the determinant here in terms of some numbers that we'd be working out. Now to attach some numbers to our example here. So we start with our determinant, our multivariate solution, and incidentally I'm using MapleSoft here for all my calculations. So this is my determinant here, that 3x3 matrix essentially. So what I do here with that determinant, the solution here, what I do is I take a Taylor expansion here of the determinant, and it's really a 2-degree expansion here at some specific quantities that we're looking at, that x or m here at 69.68 and y or the labor here at 78.49. Okay, so when I do that and I do my Taylor expansion or Taylor series on this determinant multivariable solution, I'm going to come up with a volume plane essentially. I'm going to have some quantity here, and then it shows here a negative amount here of a certain quantity times y, which is really my labor, minus a certain quantity times x, which is my material. So that's from this I can plot really a volume or a plane here. So if I just put my numbers as those x and y values into this volume plane, or this linearization here essentially of my determinant multivariate solution here, I'm going to come up with a determinant value here of 497,300. Okay, so that represents, going down to our figure here, that represents with our determinant here that we have I've plotted out here, it represents this point here. And then you can just see I run some tangent lines up here just so you can see how they fit into the determinant function. And that was that mid-range point here. And you can see we have our increasing, actually it's a decreasing values of our determinant going in this direction here, just to make that point. So I would have put that plane, if we move down here, I would have put that plane here that I calculated out using that Taylor expansion here, the y and the x value, and then that quantity here. I would have put it here, but it's really on the underside of the determinant function here. It would be a tangent plane or tangent volume plane on the underside. So these little yellow things here, those would be that x and y or m and l vectors here of those amounts, and then you have some quantity here, a quantity that you're dealing with. But what it really represents is a volume here, 497,300 volume. And you can see it's going, I have tried to lay it in respect here to the determinant function here. I've just got the underside shown. It's pointing in this direction here. Okay, so that's for that specific points. And if we just expand on that, if we move up here and just look at the other points here, so looking at that first point that we have here, say right up here, that initial point where you have that real steep descent here, that would be a point here of 6.9 something of m or x here, and y or l here would be 7.8. And again, I did a Taylor expansion here, a Taylor series on that multivariate solution here, second degree, and I came up with some x and y, a plane here, essentially a plane here, representing by this, at this point, at this initial point here. So if I put in those, looking at that first point, at this point 6.9 and 7.8, plug that into my Taylor expansion here, or that Taylor series here, I come up with 7.528 tenth of the sixth, or to be like, we'll look at that as 7,528,000 essentially. Okay, so that's for that point here. And then if I put in that second point, we already looked at it, this second point down here, that blue one, that was that Taylor expansion of 69.68, 78 here, y 78 here, and did that Taylor expansion here based on that formula we had up here. We'll come up with a new plane here, plane defined by this green surface here with those two little yellow vectors sticking out for material and labor, or x and y. So plug it in, put those x and y values here into this Taylor expansion or this Taylor series, and you're going to come up with a 4.97 or 493,000, 97,000, excuse me, 300 here. So that's really represents the volume or the volume area here of this second plane that we're looking at. First one was up here, second one here, and then the third one, same thing. Just do a Taylor expansion. In this case, I had x equal to, or material equal 174 units, and y equal to 195 units, or L here at 95. Second degree expansion, I come up with this equation here for the x and y, or material and labor here. And that's really the equation for the tangent plane, or this tangent volume that we're looking at. So you can see the point is here, we did a determinant multivariate solution, leaving in just looking at the algebra, leaving it there, not breaking it down into a matrix. And then after just knowing that, then we could come in here and we could do a Taylor expansion on that here, and it gives you the plane here. And it's easy to see here just by plotting those planes. You can understand what is going on here with the determinant here. So just looking at, going back to our path here, that gradient path, or our determinant path here, where we have started out with this initial point here, that first point that we have here, and that was at 6.9 of material and 7.8 units of labor. We have a quantity of 7,528,000 here. It really represents a volume, or a volume at that specific point. And then moving down to our next point here, what was that, 78 unit, 69 of material, 78 here of labor. We come up with 497,300. And then the third point here was, that last point, it was 178 or something, yeah, 174 and 195 here, 168,700. So these are really volumes that we're looking at. But by taking that determinant here and leaving it in an algebraic form here, and then doing a Taylor series against the algebraic form, we can come up and we can attach a plane, or a tangent plane essentially, to each of those points here, and it gives us a little better understanding of what a determinant is here. Now, there's a lot to be said about determinants by going in, and we will do that in other videos here, looking at the matrix itself here, and a whole lot of other eigenvectors and eigenvalues and so forth here. But this is really just the basic here, where you can go in, you can take and come up with, in this determinant here was based on a second degree changes here. Those are second degree partial derivatives or changes. And that's really what we were looking at here based on this determinant. It's based on the second degree partial derivatives here of changes in our production function here. Okay, so that'll pretty much end our discussion here, and we'll be looking at determinants further here and using them and attaching vectors and all kinds of other quantities to determine these determinants based on a matrix. Now, we just used some linearized here, our determinant based on an algebraic solution. We linearized it, and we were able to come up with some tangent planes essentially that we could attach to our function so we could see what's going on. Okay, so that'll end our discussion.